Now that we're comfortable adding, subtracting vectors in 2 dimensions and 3 dimensions, we can move on to some more advanced operations that we can perform on our vectors. The first of which is going to be the dot product. Now for the dot product and the cross product coming up, we can only perform these operations on 3-dimensional vectors. I, j, and k components are required. If we're working in 2D, really it's implied that the k component is going to be 0. So even though the k component is 0, we still have to explicitly include it if we are trying to do dots and cross products with 2-dimensional vectors. So what does a dot product do? Well, roughly, it's going to calculate the magnitude of one vector that lies in the direction of another vector. So that's not really saying much at this moment, but actually we've already kind of done the dot product before. If we think back to how do we put things into Cartesian component form, well, we're trying to find how much of this vector lies in the x direction, how much lies in the y direction, and that's what the I component and j component are telling us. The dot product is kind of generalizing this a little bit because this can work without having to be along a coordinate axis. We're along some arbitrary axis, as we'll see in the upcoming pictures. So how much of a vector is going to lie in the direction of another vector, but that other vector can be arbitrary and not lie just along a coordinate axis. So let's first talk about how do we do the calculation, and then we can talk about graphically what does this look like. So a dot product requires 2 vectors as the input, and the output is going to be one scalar. So 2 vectors go in, one scalar comes out. And the dot product, for this reason, is also called sometimes the scalar product or the inner product. In this class, though, I will always refer to it as the dot product. But if you see in linear algebra books the scalar or inner product, it's the exact same thing. So different ways that we can calculate this, the way you might have seen it before in a physics class, is that we could take our 2 vectors, A and B, and we have this dot between them. Now, we don't want to confuse this with multiplication. We can't simply multiply 2 vectors together. We can multiply 2 scalars, we can multiply a vector and a scalar, but this can never mean multiplication if it's 2 vectors being dotted here together. So A dot B, we would call it, is equal to, now by this kind of physics definition here, we can take the magnitude of vector A, which we know how to find, the square root of the sum of the squares of its components, times the magnitude of B, times the cosine of the angle between A and B. So in this kind of graphical thought, when we have these 2 vectors in space, if we can find the direct angle between them and take the cosine, we can calculate the dot product this way. I'd say for this class, this is less often how we are going to be computing the dot product, because we are going to be working in Cartesian components. There's easier ways to do this calculation. We don't need to actually know the angle measured between these 2 vectors. So really the second line is what we're going to be using more. If we have vector A, now unfortunately I'm using A and B in 2 different ways here. So let's just say this vector A we can express as AI plus BJ plus CK. And then this vector B we could express as DI plus EJ plus FK. So again, sorry for the A and the B being overused. This A is just some number, this B is just some number. So we have our first vector dotted with our second vector, and we're in Cartesian component form. So when we're in Cartesian component form, we dot them together, and the process is going to look like this. We are going to multiply basically the like components. So a vector 1, its I component is A, and for vector 2, its I component is D. So it's going to be those coefficients multiplied together, A times D, plus the J components multiplied together, B and E, plus the K components multiplied together, C times F. So we have this A times D plus BE plus CF. Notice again here, A and D are scalar, B and E are scalar, C and F are scalar, and we're adding them together. So we have a scalar as our result. We have a vector dotted with a vector, and then the right-hand side here is again a scalar. And one thing to note about the dot product is actually the order that we dot in does not matter. If we go again up to this definition here or the first one, the order should not matter. Whether it's, if we switched vector 1 and vector 2, we would have d times a, which we know multiplication is the same way. A times d is the same as d times a. E times b is the same as b times e. And f times c is the same as c times f. So the order of the dot product does not matter. As a note, when we look forward to the cross product, in the cross product, the order does matter. And the dot product is going to tell us, again, because in that first definition, the dot product depends on the cosine of the angle between these two vectors. If our two vectors are perpendicular to each other, the dot product will always yield 0. And we can see here from this kind of physics definition, the cosine of 90 degrees is going to be 0. So the right-hand side is 0, which means that the left-hand side is going to be 0. So perpendicular vectors have a dot product of 0. And this dot product can be a quick way to check for if two vectors are perpendicular. If the dot product is 0, they're perpendicular. If it's anything other than 0, then they are not perpendicular. So let's look graphically at what are we actually doing when we take the dot product and how can we use it to find the direction of one vector in terms of another. So if we have some vector A in red and some vector B in blue here, I don't have the coordinate system drawn here, but let's just say it's x to the right, y is up, but really it's going to be coordinate system independent here. All right, so what we can do is we can break the A vector into components, like we do when we are breaking it into the I and j components, but here what we call kind of the basis is going to be the B vector. And here B is off at some oblique angle, trying to imply it is not solely in the x or solely in the y direction. So we can find what we call A parallel. So that is going to tell us how much of A lies along the B direction or the B vector. So notice that A parallel in this picture is shorter than B because A parallel is often called the projection of A onto B. So how is it being calculated? So A parallel is going to be vector A dotted with not B, but the direction of B. So notice here it's dotted with U hat B. So B is going to contain its magnitude and its direction. We don't want to dot it with that. We want to dot it with just the direction of B. So U hat sub B is the unit vector along the direction B. Now, if we think of what we've been doing with breaking vectors into component form, really this is the first step when we are putting a vector into component form is really we're dotting it. Let's say we want the x component. Well, we're dotting our vector, let's say A, dotted with I. Now remember, I hat, j hat, k hat, well, they have a hat over them. They are unit vectors. But specifically, I hat is the unit vector that has 1 in the x direction, 0 in the others. J hat is the unit vector that has 1 in the y direction, 0 in the others, and k hat has 1 in the z direction, 0 in the others. But now we're extending it to a vector pointing in any direction, so we can dot it with that unit vector that might have x, y, and z components to it. So the amount of A parallel is A dot U hat B. Now, if we want to know that as a vector, we're now going to take the result we just found, A parallel, and we're going to now multiply it by U hat B. So again, we're allowed to do this. A parallel is a scalar because we're taking the dot product of two vectors, which is a scalar. And now down here, we have a scalar times a vector. Well, that's allowable. It's just going to be multiplying each component of the unit vector by this scalar A parallel. Or we can do it all in one step, but I think it's easier to break it up. A dot U hat B, that result times U hat B, and that is vector A parallel. Now, if there's a parallel component, there's also this perpendicular component to it as well. So we can deconstruct A into its parallel and perpendicular directions. Again, thinking in a 2D environment, this is exactly what we're doing when we're finding the I and the j components. But there specifically, the parallel would be how much is along the I direction, and the perpendicular would be how much is along the j direction. but we can reconstruct our vector by going along from the start of A along A parallel and then along A perpendicular, or we can start at the tail of A and follow it all the way to the arrow tip. So we have two alternate ways to go from the start position to the end position. And we know that because this is going to always make a right triangle, since the parallel and perpendicular directions are perpendicular to each other, well, using right triangle Pythagorean theorem, we know that the magnitude of A squared is equal to the magnitude of its legs, the sum of the magnitude of its legs squared.